Case study: Overcoming adversarial attacks, strengthening machine learning defenses in cybersecurity. The integration of machine learning algorithms into critical applications demands a rigorous examination of their vulnerabilities, especially in the face of adversarial attacks. In the heart of Silicon Valley, a cybersecurity firm named CipherGuard faces a daunting challenge. The firm, renowned for its cutting-edge threat detection systems, employs machine learning models to identify and neutralize cybersecurity threats. The firm's CTO, Jessica Lee, and her team of data scientists are about to discover the harsh realities of adversarial machine learning. Jessica's team had recently developed an advanced intrusion detection system based on deep learning algorithms. The model had shown remarkable accuracy during testing, identifying and categorizing potential threats with unprecedented precision. However, within weeks of deployment, Jessica received alarming reports indicating that several sophisticated attacks had bypassed the IDS. How could this be possible when the model had performed flawlessly in controlled environments? This conundrum led Jessica to recall the seminal work of Seghetti et al., which revealed the susceptibility of machine learning models to minor perturbations in input data. These perturbations, often invisible to human eyes, could cause models to make erroneous predictions with disturbing confidence. Jessica convened an emergency meeting, bringing together her top data scientists and cybersecurity experts to investigate the breach. The team quickly identified that the attackers had employed evasion attacks, crafting adversarial examples that fooled the IDS. This discovery was a revelation, underscoring the pressing need to understand and mitigate such vulnerabilities. They pondered, how could adversarial examples so effectively deceive a model trained on vast amounts of data? Reflecting on the study by Gross et al., the team realized that adversaries had subtly altered the features of their malicious software, successfully evading detection. Jessica's team examined the attack vectors and noticed that the perturbations were minimal, yet impactful. This raised another critical question. What specific changes had the adversaries made to evade detection, and how could the team counteract such sophisticated techniques? To reinforce their defenses, the team considered adversarial training, following the approach presented by Goodfellow et al. By incorporating both clean and adversarial examples in the training set, they aimed to enhance the model's robustness. However, this strategy posed a dilemma. Adversarial training is computationally intensive, and the team worried about its scalability and effectiveness against unseen attacks. They asked themselves, can adversarial training provide a long-term solution, or will adversaries continually evolve to outsmart the defenses? While grappling with evasion attacks, the team also faced another formidable challenge: poisoning attacks. These attacks, as described by Steinhardt, Ko, and Liang, involved the injection of malicious samples into the training data, corrupting the model from its inception. Jessica discovered that the attackers had subtly introduced poisoned data, skewing the model's learning process and leading to false positives and negatives. This sabotage compromised the IDS's reliability, and the team questioned, how can they safeguard their training data from such covert manipulations? Given the urgency, Jessica's team explored robust optimization techniques inspired by Madri et al. This method framed the training process as a min-max optimization problem, aiming to minimize the worst-case loss under adversarial conditions. Although promising, this approach further strained their computational resources. They debated, is the increased computational burden a justifiable trade-off for enhanced robustness? Parallel to these efforts, the team investigated methods to detect adversarial examples proactively. Feynman et al. Proposed using kernel density estimation and Bayesian uncertainty to detect adversarial inputs. Simultaneously, Xu, Evans, and Chi suggested feature squeezing to limit the search space available to attackers. Jessica's team implemented these techniques, hoping to add an additional layer of defense. They pondered, can these detection methods significantly reduce the risk of successful adversarial attacks, and how effective are they in real-world scenarios? As they delved deeper, Jessica's team recognized the need for a theoretical framework to understand adversarial risks comprehensively. Bertsimas, Delarue, and Misic proposed adversarial risk analysis, using game-theoretic approaches to model the interactions between attackers and defenders. This framework provided valuable insights into balancing accuracy and robustness. The team questioned, how can game theory inform their defensive strategies, and what trade-offs should they consider to optimize their model's resilience? The implications of their findings extended far beyond the confines of cybersecurity. Jessica envisaged the potential catastrophic consequences in domains like autonomous driving and healthcare. In autonomous driving, adversarial attacks could mislead image recognition systems, causing fatal accidents. In healthcare, manipulated diagnostic models could lead to incorrect treatments. The team reflected, how can their learnings from AML be applied to safeguard other critical sectors reliant on machine learning? Despite their progress, Jessica's team faced a persistent challenge: the adaptive nature of adversaries. Attackers continuously evolved their strategies to defeat existing defenses. This necessitated ongoing research and innovation to stay ahead. The team wondered, how can they develop a dynamic defense system that adapts in real time to emerging threats? To address these questions systematically, Jessica's team formulated a detailed analysis and devised potential solutions. 1. Evasion techniques. By studying the perturbations used in evasion attacks, the team identified patterns and developed more robust feature extraction methods, reducing the model's vulnerability to minor alterations. Integrating adversarial training enhanced the model's resilience, though they remained mindful of its computational demands. 2. Poisoning defenses. To safeguard against data poisoning, the team implemented stringent data validation protocols and employed anomaly detection systems to identify and eliminate suspicious training samples. This proactive approach mitigated the risk of compromised training data. 3. Robust optimization. Adopting Madrigal's robust optimization, the team balanced the computational costs by employing distributed computing resources and optimizing code efficiency. This ensured the model's robustness without overwhelming their infrastructure. 4. Adversarial detection. Implementing detection techniques like kernel density estimation and feature squeezing, the team successfully identified and filtered out adversarial examples, enhancing overall security. 5. Theoretical insights. Utilizing ARA, the team adopted a game-theoretic perspective, understanding adversarial behaviors and strategizing accordingly. This holistic view informed their defense mechanisms, optimizing the balance between accuracy and robustness. 6. Cross-industry applications. Jessica's team collaborated with experts in autonomous driving and healthcare, sharing insights and developing domain-specific solutions to mitigate AML risks. This interdisciplinary approach fostered innovation and resilience across sectors. 7. Adaptive defenses. To counter the evolving nature of adversarial strategies, the team embraced continuous learning and real-time monitoring. They developed adaptive algorithms that self-improved based on new threat data, ensuring preparedness for future challenges. Jessica's team documented their journey, creating a comprehensive framework for understanding and mitigating adversarial attacks. Their experience underscored the critical importance of robust machine learning models, not only in cybersecurity, but across all domains reliant on artificial intelligence. By addressing these challenges head-on, they set a precedent for future research and development in adversarial machine learning, paving the way for more secure and resilient AI-driven systems.